Well, first of all, thank you all for being here so early in the morning. And thank to the organizers for putting together such an amazing event and for giving me the opportunity of presenting my research. First of all, can everyone hear me if I talk like this? OK. So what I'm going to talk about today is a project that I worked on with Bertrand Eynaert, Elba Garcia-Failde, Danilo Levansky, and Riccardo Schiappa, and which led to this paper here. It was a project motivated by a physical problem, but I think it led to some really nice mathematical results. And this is what I'm going to present today. So by now you should be quite familiar with most of what appears in the title. So you've seen several talks about topological recursion and Weil-Petersson volumes. And I will try to clarify what I mean by non-perturbative. So let me give you a brief outline of the talk. First, I will introduce Weil-Petersson volumes and their relationship with topological recursion. Then I will give you a lightning review of Resurgence. But it will be really basic concepts from Resurgence, nothing particularly deep. And then I will conclude with explaining what I mean by non-perturbative topological recursion and giving you some results, mainly in the form of Larinos asymptotics of Weil-Petersson volumes. OK, so let me start by introducing Weil-Petersson volumes. You've seen them already quite a few times. I will be very quick with this. The idea is to introduce the moduli space of genus G hyperbolic Riemann surfaces with n geodesic boundaries of lengths B1, Bn. And so B1 and Bn, these are real numbers, positive real numbers. They are the length of the geodesic boundaries. And G is a positive integer, which is the genus. And on this moduli space, we can introduce quite naturally a symplectic form, which is called, I will call omega Weil-Petersson. And it's natural to define the Weil-Petersson volumes, which will depend on the boundary lengths B1, Bn, as integrals of this symplectic form over the moduli space. But there is also a way of computing them, which is by performing some integrals over mg n bar, the moduli space of curves. There will be integrals over a specific combination of the first kappa class and psi classes, which I will write now. Oh, this is probably very low for most people. I will raise the board later. So for those of you who are not super familiar with these concepts, I will actually not need this definition of Weil-Petersson volumes at any point of my talk. I just want to illustrate how they are originally defined. And so these exponentials here will actually contribute a finite number of terms, because as soon as this product of kappa 1 and psi classes saturates the dimension of the moduli space, which is 3g minus 3 plus n, well, higher terms will give 0. So we can actually write this down as a sum, a finite sum. a sum of some intersection numbers of the kappa class with, psi classes, which I'm here writing using Witten's notation. Multiplying some powers of the BIs. So the idea is that this is a finite sum. It will be a polynomial of degree 3g minus 3 plus n in the BI squared. So nothing particularly crazy. It's very explicit. The problem is to compute them directly using this expression as an integral over mgn bar of some intersection numbers. This will be very hard. So if you want to go to high topologies, immediately you realize it's a very hard computation. And so we need some other way, more efficient way of computing them. So just to make contact with the physics motivation of this project, these Weil-Petersson volumes appear in models of two-dimensional quantum gravity. And essentially, well, in a specific model that is called JT gravity, which is particularly popular among theoretical physicists right now. And intuitively, the reason why they appear is because in this model, there is a notion of integrating over all hyperbolic surfaces. And so they appear quite naturally in that context. But as I said, they are very hard to compute directly. And they were very hard to compute until Mirzakhani in 2007, if I remember correctly, came up with a recursion for them. So you've seen this kind of drawing already several times, I think, during this conference. I will do it again, maybe a bit lower. Okay, so the idea of Mirzakhani's recursion is to start, you want to compute some VGN. So let me draw one with a certain topology. This one has 4 boundaries and genus 3. And the idea is to remove pairs of pants from it in all possible ways, in such a way that it can be expressed as pairs of pants glued to lower topology Weil-Petersson volumes. Plus, for example, this possibility. And if you remember, for example, Sevran's talk from yesterday, you saw a very similar drawing for visualizing topological recursion. And this is exactly what's going on. So in 2007, Einard and Orantin realized that this is just a realization, a specific realization of topological recursion. And let me, well, first of all, this recursion is already an extremely useful tool because it allows you to compute Weil-Petersson volumes recursively. And let me give you a couple of examples. Well, there's a very basic one, which is V03. And then you have 1, 1. B squared. So very explicit expressions. And when Einard and Orantin realized that this was topological recursion, of course they had to give which spectral curve realizes Mirzakhani's recursion as a topological recursion. So let me remind you what topological recursion is. It's a recursion that takes as input a spectral curve, which is made up by a Riemann surface sigma, two functions defined on sigma, x and y, and by differential b. And the specific spectral curve that Eynard and Dorantin found reproduces a Mirzakhani's recursion in the form of topological recursion takes sigma as CP1, X, and Y can be parameterized using a variable Z living on CP1, which is gives X equals to Z squared, and Y is the sine function Z. And here, well, I better put B here. As I said, it's a bidifferential, which is actually a very common one. It's called the Bergman kernel. And now, so what is the idea of topological recursion? You have a spectral curve, you use it as an initial condition to run a recursion, which generates for you multidifferentials omega gn, which are also called the invariants of topological recursion. And okay, so you run topological recursion with this spectral curve, you obtain some omega gns. Let me give you some of them. Omega 0,3. Again, this is all very explicit. Omega 1,1 as well. Sorry. Better like this. And so what is the relationship between these omega gns computed with this specific spectral curve and the Weil-Petersson volumes I wrote there? It's just a Laplace transform. So you Laplace transform the Weil-Petersson volumes, and you get the omega gns, and you anti-Laplace and you go in the other direction. So okay, we are quite happy. We have a recursion, we can just run it and generate as many numbers as we want. What is the problem? Well, there are two main issues with this. First of all, just through this recursion, it's not easy for example, to get information about the Larinos behavior of these numbers. And we saw already in this conference how much we care about Larinos behaviors of enumerative objects. And, oh yeah. And secondly, well, the second problem is actually more of interest for physicists, and I will get to it actually a little bit later. So, first problem, Larinos behavior. So as I said, this recursion is not ideal for understanding the Larinos behavior of Weil-Petersson volumes, but there are already some results in the literature about their behavior. Well, I forgot to introduce some notation. Let me do it here. So I will refer to VGN without writing explicitly the dependence on the geodesic lengths as the VGNs evaluated at all boundary lengths 0. Okay? So the results that we have about the Larinos behavior of Weil-Petersson volumes are by Mirzakhani and Zograff, who gave Larinos asymptotics at fixed n of the VGN I just defined there. So there is an overall constant that I call A0, then a factorial growth, then there is an exponential part, 2g minus 5 halves plus n. And they also gave actually the first subleading correction to this behavior, which can be written in this form. Sorry, this will be a bit long and maybe not particularly illuminating, but it's just to show you the state of the art. And well, those of you who are very familiar with with their results might notice that they are not quite written in this way in their paper, so I have already massaged them a bit. And I did so, well, in such a way that in this form I already recognize a structure that you might remember from Alessandro's talk from 2 days ago. So if you remember the Larinos asymptotics of intersection numbers that he gave 2 days ago, they had a very similar structure, essentially the same structure. And so this constant here, A0, they were not able to prove its value. It is conjectured to be square root of 2 pi to the 3 halves. And well, there is very good reason to believe this is true, but they were only able to obtain it numerically. And then there were some results by Kimura concerning the Larinos asymptotics of Weil-Petersson volumes with boundary lengths different from 0. And let me, well, write it here. Yeah. VGN. Again, we have an overall constant. So same factorial growth as expected, same exponential contribution, but then of course we have a part that depends on the boundary lengths, which is encoded by this function that I call S. Let me define it here. It's the ratio between the hyperbolic sine of x over 2 and x over 2. Okay? And well, Kimura was only able to give conjecturally, so he gave some arguments for n equals to 1, 2, 3. And from those 3 points, he extrapolated a general formula. But of course, well, the constant here is still conjectural, and the general n expression is conjectural, and he was also not able to give anything for subleading corrections. So, okay, this was the state of the art. And one question is, okay, can we improve on this? Maybe give a recipe for obtaining analytically this constant and an algorithm for computing subleading corrections. And there is a second problem, which, as I said, is maybe more of interest for physicists, which is, okay, the quantities you want to compute in 2D quantum gravity are actually of the following form. Let me write what we call the free energy, for example. It's written as a power series in a parameter h bar. And in terms of the Weil-Petersson volumes with no boundaries. Now, from what I just wrote here, the Larinos asymptotics tell us that those numbers grow like 2g factorial. So this is obviously a divergent power series. It has 0 radius of convergence, And physicists would like to actually make sense of this object. So what do I mean by making sense? I mean assigning an analytic function in h bar to this object that is at least analytic in some sector of the complex plane. And so, okay, we have two problems essentially, and it shouldn't come as a huge surprise that both of them can be addressed in the framework of Resurgence. So let me maybe erase something. So I can move to the second part of the talk, which is a very quick review of the tools we need from Resurgence, some of which were already introduced by Alessandro 2 days ago. Okay, so the idea of Resurgence is actually, well, one of the main ideas. This is terrible. One of the main ideas is to actually make sense of divergent power series, or if you want, of formal power series whose coefficients grow like a factorial. And so let me give you a toy example of this, just to fix the ideas. Let me introduce a formal power series phi in some parameter h bar. H bar to the g times some coefficients, and we have that the coefficients grow like g factorial. Okay, sorry. Okay, so how do we make sense of this object? Alessandro already gave you half of the recipe that Resurgence proposes for assigning an analytic function. And actually, sorry, let me denote this by phi tilde. This procedure is called the Borel-Laplace resummation. Alessandro already showed you the Borel part, and here I will, well, remind you what it means and also give you the Laplace part of the resummation. So the Borel part simply defines the Borel transform of this formal power series as an object called phi hat of another variable s, which is simply obtained by, it's almost naive as a proposal. You just remove by hand the factorial growth of the coefficients of the formal power series you started from, in such a way that you get something that is convergent at least on a disk centered at the origin. And what Alessandro told you 2 days ago is that typically the Borel transform of a divergent power series will have singularities in the complex plane of the S variable, which we call the Borel plane. And well, Alessandro stuck to logarithmic singularities, and this is what I will do too. And this defines for you the class of simple resurgent formal power series. So simple resurgent formal power series are characterized by having only logarithmic singularities in the Borel plane. And let me remind you what I mean by logarithmic singularity. I mean that around a certain point A, it will behave like, well, I choose this normalization, 1 over 2 pi I log of S minus A times, let me call this phi 1 hat, a holomorphic function at the origin, which we call the minor, plus something that is holomorphic at A, and which we don't care about. So as I said, this is holomorphic at the origin, so we can write its Taylor expansion, which will, And actually, I'm allowing another exponent here, which I call beta, which just tells me that this power series doesn't need necessarily to start from s to the 0. And some coefficients phi 1g. Okay. So this is half of the game, the Borel transforming the original formal power series. And let me also give you an illustration of this example in the Borel plane. You have a singularity at the point A here, which will be a log singularity, so there will be a logarithmic branch cut in the Borel plane. Now, I said this is only half of the game because now we want to go back to the h-bar plane, possibly carrying with us an analytic function, at least in some sector of the h-bar plane. And this is done by Laplace transforming the Borel transform. So, essentially, you act with the Laplace transform, which now I label L0 for a reason that will become clear in a second. And I obtain a function, phi of h bar, which is given by the integral from 0 to infinity of ds e to the minus s over h bar of my Borel transform. And there's a theorem that states that if we do this procedure, this analytic function phi of h bar will have phi tilde of h bar, our original formal power series, as its asymptotic expansion. So we got exactly what we wanted, some analytic function which has this as its expansion. Now, of course, I'm hiding a lot under the carpet here because, okay, when can we actually do this Laplace transform? You need to have some conditions at infinity that make this integral converge. But let's assume that this is satisfied. But also, you don't have to encounter any singularity on the real axis, right? And for the moment, in my toy example, I placed A away from the real axis, but in principle, it could be there. Also, this defines for you an analytic function, but not in a sector of the complex plane, rather on an array, on the real, for real values of h bar, essentially. So if you want to obtain an analytic function in a sector of the complex plane, you can imagine of doing what are called directional Laplace transforms. So you perform this integral on an array that is not necessarily the real axis. So let me put L theta here and e to the I theta infinity here. So what I was originally doing is integrating along the real axis, but now imagine we integrate along this ray here. And so we really span the whole complex plane with these directional Laplace transforms and produce something that is analytic on a sector of the complex plane. But now what happens when we find a singularity? Well, imagine we want to avoid the singularity, so we can perform the directional Laplace transform just below for an angle theta minus, and just above the singularity for an angle theta plus. And actually, well, the two resummations just below and just above singularity in the Borel plane will be different, and it's intuitive why, because there is a logarithmic branch cut between them. And if you try to compute what is the difference between the two Laplace transforms, so acting on our Borel transform, this is a simple exercise you can do given this singularity structure and the definition of the Laplace transform. You realize they will give you a contribution of this form, e to the minus a over h bar times a power series in h bar, which contains exactly the coefficients of the minor. So, okay, we started from wanting to resum a formal power series in H bar, and we ended up with contributions that are not formal power series in H bar because they are multiplied by this e to the minus a over H bar, which is clearly has clearly an essential singularity at the origin. So this cannot be expressed as a power series in H bar. So okay, these objects, we call them trans-series. And what I will call them, and what they are called typically in the literature, is the non-perturbative sector associated to the singularity in A. Okay, why non-perturbative? Because, as I said, this cannot be expressed as a perturbative expansion around the origin. Okay, so we found Resurgence teaches us that whenever you are dealing with formal power series and you try to resum them, you will inevitably encounter objects that are not formal power series anymore. We call them non-perturbative sectors. And okay, so far this might seem very obscure. There's a lot of physics interest in these objects, but for our purpose of understanding Larinos asymptotics, why are they interesting? So, and you might ask, yeah, why did you introduce this very mysterious object when Alessandro 2 days ago taught us that you just need information about the Borel plane singularities to compute Larinos asymptotics of the object that you're interested in? And so let me motivate this for you in a minute. Okay, so the first one. So what I want to do is remind you, first of all, of the theorem that Alessandro showed you 2 days ago, which gives you Larinos asymptotics in terms of the Borel singularity data of your problem. And this, well, this I don't need anymore. So the theorem is stated as follows.
Can you remind us where the beta comes from? It's just part of your function?
Yeah, beta is just the statement that that Taylor expansion of phi hat does not necessarily start from a constant, but it might start from some positive power of S.
But this is the general situation.
Yeah, the most general, actually, I'm not being extremely general. The most general situation also, phi tilde might not start from H bar to the 0. But for the moment, for the purpose of this toy example, I'm just making phi tilde start from H bar to the 0, and the minor start from S to the beta. Okay, but it's just to make it slightly more general than what Alessandro showed you 2 days ago, but yeah, the most general situation is even more general. So the theorem states that if that is the kind of singularity we have in the Borel plane, then the large G asymptotics of the coefficients of the formal power series we started from will be of this form. Actually, pi I. There will be a factorial growth where now beta appears. So this is the reason why I wanted to put beta there, because it will appear also in the Larinos asymptotics. There will be an exponential term dictated by the position of the singularity in the Borel plane. And then you will have all the coefficients of the Taylor expansion of the minor. So you will have phi 0, 1, giving you the leading contribution. Then you will have A over G minus beta minus 1, phi 1, 1, A squared to 1 plus order of 1 over g to the third. Okay? So I just wrote for you the first few terms to illustrate the structure of what appears in these resurgent large G asymptotics. Now, okay, at this point it's very legitimate to ask, okay, why did you go through all of this? Why did you introduce trans-series and non-perturbative sectors when they seem to contain the same information that the singularities in the Borel plane contain? And the answer is simply that very often we have no idea of what is going on in the Borel plane. So we cannot perform the Borel transform analytically and obtain a closed form for the Borel transform of a formal power series we are interested in. Sometimes the best we can do is compute some non-perturbative data with means that might come from an integral representation of the object we started from. So to give you an intuition of how these non-perturbative sectors might arise, imagine you got your formal power series you started from an ODE. So you're trying to solve an ODE using a power series ansatz. The non-perturbative sectors will arise as other solutions to that ODE. If you are obtaining your original formal power series from, for example, doing the saddle point approximation of some exponential integral, then those non-perturbative sectors will arise as saddle point approximations around other saddles. So you can understand how these kind of terms arise, and you can also understand how very often you cannot really just Borel transform what you have and study the singularities in the Borel plane. And this is precisely the case, for example, in matrix integrals and in the case of Weil-Petersson volumes. So in the case of Weil-Petersson volumes, unfortunately, we cannot just look at the Borel plane and say, okay, there's a singularity at position A with certain Taylor expansion for the minor. But we have a recipe for computing non-perturbative data. And since non-perturbative data contains the same information as Borel singularities in the Borel plane, we can actually recover Larinos asymptotics of Weil-Petersson volumes through this other strategy. Okay, so this brings me to, first of all, let me now erase here.
While you are erasing a terminological question, why is it called non-perturbative?
Oh yeah, non-perturbative is, probably it's more physicist terminology for saying that you cannot really Taylor expand at the origin this e to the minus a over h bar. Okay. Okay. As I said, this is something we are interested in, this formal power series, and now it turns out that we are also interested in another object which has the form e to the minus some complex number a over h bar times another formal power series h bar to the g plus beta and some coefficients which I will call vg01. Okay? So what I will try to show you in the following is, okay, if we are able to compute a and these new coefficients vg01, we can actually fill in the blanks in this resurgent large G asymptotics and obtain Larinos asymptotics for Weil-Petersson volumes. Okay, so I'm very sorry that this recipe will appear as completely out of the blue. I cannot give you a proof for this recipe because it would take me too long. I can tell you that it's inspired by matrix integrals. So there is it takes very old ideas about computing non-perturbative contributions to matrix integrals and applies them to this particular case of Weil-Petersson volumes, which is not a matrix integral, but shares many features with matrix integrals. So this I can erase. And this recipe that I will show you in a minute is what I call non-perturbative topological recursion. So it's non-perturbative in the sense that unlike usual topological recursion, which computes for you coefficients of some formal power series, this recipe computes for you non-perturbative sectors. So the idea is, okay, you take the omega GNs you computed with topological recursion, with the spectral curve that I have erased a while ago, I think, and you package them in a way that at first sight might seem quite exotic. So you define this function of h bar and x, psi, which we sometimes call a wave function, as the exponential of a sum for g greater than 0 and n greater than 1 and you integrate all the omega GNs n times, so in all of their variables, from minus z to z, keeping in mind that x equals to z squared. So the x dependence of this object comes from the z dependence here. Okay, I will give you 10 seconds to digest this formula. It's just a very apparently weird repackaging of the omega GNs. But if we run topological recursion, we can compute several of these guys, and we can essentially give an expansion in h bar of this object, okay? And for those of you who are familiar with the language of generalized cycles and shifted partition functions and so on, this will be probably only for the experts in topological recursion. This you can denote as the partition function of the TR partition function associated to the original spectral curve shifted by a cycle that goes from minus z to z, divided by the partition function associated to the original spectral curve. Okay, this will be very obscure for those who don't know about this terminology, but it might be useful to the experts. Okay, so what do we do with this weird object I just defined? You perform an integral. So this f1 of h bar that I wrote there will be given by an integral over a certain contour I that I will specify in a minute of this wave function. The contour I is a steepest descent contour that passes from the first nodal point of the curve. So remember, let me write again the curve. It was defined by, well, x equals z squared and y equals to sine 2 pi z over 2 pi. So this curve has infinitely many zeros, which are infinitely many nodal points in this double covering of CP1. And so for example, the first zero will appear at x equals to 1/4. So we want a contour that is a steepest descent contour. For those of you who don't know what a steepest descent contour is, just a contour that dies off at infinity in such a way that this integral converges and passes through x equals to 1/4. So you can do the saddle point approximation with this integral, and what it gives you is something like this: I over square root of 2 pi, square root of h bar, e to the minus 1/4 pi squared, 1 over h bar. And then, so you immediately see, well, there is an overall constant, and this term e to the minus 1 over 4 pi squared, 1 over h bar, is exactly of this form here. So we have recovered the non-perturbative term. And then there will be a formal power series in h bar of the form So I gave you the order h bar term, but of course you can do this very efficiently. Actually, this might seem very abstract, but this is something you can program with your favorite software. It will spit out for you as many numbers as you want here, and so as many non-perturbative data, and which translates into as many subleading terms in the Larinos asymptotics. So I think the Larinos asymptotics are in the first board. Oh my God. Perfect. So, okay. Now, okay, up there I have the theorem that gives us large G asymptotics for simple resurgent formal power series. Here I have what is already known about Larinos asymptotics of Weil-Petersson volumes. If you plug these values here into the board into the equation up there, you immediately notice that you recover the Mirzakhani-Zograf result for n equals to 0, even including this constant A0 that is so far only obtained numerically. So you plug essentially I over square root of 2 pi in place of phi 0, 1 up there, and you obtain the constant. And okay, you keep plugging in things. This is A, 1 over 4 pi squared. You recover exactly the formula for n equals to 0. Topological recursion allows us to go further. So there is an object called the loop insertion operator, which I denote by delta z, which acting on the omega gns gives us the omega gns plus 1. So it raises n by 1. And by applying recursively, iteratively, this loop insertion operator to this formula here, you obtain also the higher n Larinos asymptotics, which match perfectly the results by Mirzakhani and Zograf. And it gives us also a recursive way of obtaining all the subleading contributions. Not only this, we were able also to obtain, using the same strategy of applying iteratively the loop insertion operator, the conjectured expression by Kimura, so including this product of ratios of hyperbolic sine and x, and also subleading corrections to that one. Yes? Yeah, sure. Yeah. So, yeah, you're right. I didn't put the full literature, but yeah, that's all right. Is it for general n? I don't remember. Yeah. Okay, perfect. Okay, perfect. Okay, so well, we have that too, and and we can go beyond. So what I find nice about this procedure, which is also something that Alessandro stressed 2 days ago, is that it allows you quite easily to go to all the corrections. And in fact, well, my time is almost over. I would like also to point out that what we get here was done. Remember that this integral is done by a steepest descent contour that passes from the first zero of the spectral curve. But as I said, the spectral curve has infinitely many zeros. So in principle, infinitely many singularities in the Borel plane, which will also contribute to the Larinos asymptotics. So these ideas allow you also to explore other contributions to the asymptotics, which are exponentially suppressed with respect to the leading one, and which are very hard to see normally using other techniques. Of course, and well, this is something I would like to stress, and I don't want to hide, is the fact that all these results rest on the relatively heavy assumption that the formal power series obtained by Weil-Petersson volumes is a simple resurgent formal power series, which is not a proved result yet. So we are working on that. It's not a hopeless proof, but for the moment, we are assuming the formal power series to be simple resurgent, and then we obtain these Larinos asymptotics. And yeah, and with this, I would like to conclude.
Thank you for the talk. Yeah. So are there any questions? And if there is any, wait for the microphone because the talk is recorded.
So I was just wondering, like, is there, so in the examples that Ale had, if I remember correctly, this beta was 0, right?
Sorry, in which example?
The ones that Ale had?
Well, okay. So if one wants to be super precise or more general, as I said, one can actually consider the formal power series you start from as starting from another power, which is not necessarily 0. And in fact, you see immediately that here the power is -2, actually. And, and for the WGNs, which are the ones that compute for you intersection numbers, the power series actually has also a +n here. And this is why Ale was obtaining a factorial growth of the form gamma of 2g minus 2 plus n, because actually what appears here is the difference between, let's call it beta 0, the starting power of the original formal power series, minus beta 1, the starting power of the non-perturbative formal power series. So this is what he was getting. Here I'm getting 5 halves plus n, because I still have the -2 here and the -2 plus n for correlators, but I also get a square root of h bar here, which tells me that beta here is 1/2. So by computing -2 minus 1/2, I get this -5/2, which will be very general, I think.
Yeah, but I was wondering more like, thanks, but I was wondering more like, is there some meaning like for the fact that you get 1/2, like from the enumerative problem, for example?
No, from the enumerative problem, I have no clue, honestly. So I would say that it's going to be a very universal thing that will appear, this -5/2, because, well, from spectral curves of this kind, in which you have nodal points and you perform this steepest descent contour with a contour that passes from the nodal point, it will be inevitable that you get this square root of h bar here, and so you will get this -5/2 all the time. But I have no clue about a geometric interpretation about it.
Paolo, you mentioned that the subleading terms can be gained by some sort of recursion.
Yeah.
The only recursion I've ever heard of is topological recursion. Yeah. Can you say some words about the nature of what you mean? So, yeah, it's not a real recursion in the sense that you obtain the next one only in terms of the previous one. I would call it more of an algorithm, probably. That's a better expression. So you run topological recursion, you compute as many omega GNs as you can, and this allows you to go as far as possible in this saddle point approximation. And this is the algorithmic nature of the computation of subleading terms. So, but I want to stress that this is something you put on a computer, you let it run, and it's very, very efficient. Okay, thanks.
I would like to double check on the status of the value of this universal constant in there.
Yeah.
So do I understand correctly that you have a proof that this value is the value modulo, so...
modulo the assumption that this is a simple resurgent formal power series. Yes, exactly. So it comes, and actually, well, yeah, it comes from this value here, which in turn comes from essentially performing this saddle point integral at the leading order. So it's just a Gaussian integral that you perform. And this is why you get this, it's actually, you get this square root of h bar over 2 pi. And yeah, if one was able to prove that this is a simple resurgent function, then that the value of that constant is proved.
Is it sort of if and only if? If somebody would communicate with the value, would it imply simple resurgence?
No, not really. No, I don't think so, at least, but yeah. Yeah.
Can you say something about what happens when the boundary lines B also tends to infinity at the same time with G? Okay,
well, so it depends a bit on, it's a question of orders of limits in a sense. So if you want to take the value of the boundary lengths to infinity before looking at the Larinos asymptotics, what you get is this metric ribbon graph limit. And so you're computing the Larinos asymptotics of metric ribbon graphs, which are actually, you can obtain from just using the Airy spectral curve as a starting curve. So you will recover that with this procedure. You can also find that limit, but it will be very different asymptotics with respect to that one, because essentially, so yeah, we can talk later. I can give you more details, but the idea is that there are other singularities in the Borel plane which contribute to that particular asymptotic regime. So they will look quite different, the asymptotics.
Yes. The other day, Alessandro mentioned a lot the Airy function, and he said, for if I understood, he said that for the volume polynomials there is a function playing a similar role, but it's less well understood.
Yes.
Does it show up somewhere in your talk, this function?
So not really. So it should be a relative of this psi here, but with integrals over the omega GNs, which are computed on a different interval. It doesn't show up in my talk because, yeah, as Alessandro told you 2 days ago, it's not as understood as the Airy function, so we cannot really use it to, for example, look at singularities in the Borel plane. That's why we have to take this rather different approach for the Larinos asymptotics of Weil-Petersson volumes. I hope at some point, yeah, we hope to get some understanding of that function, but at the moment it's really hard to extract information from it.
Thank you.
Right, so can I ask one more thing about this like strange looking formula that you wrote for the F1, this like integral?
This one?
Yeah.
Yes.
I mean, is this somehow coming from the non-perturbative TR where you have this kind of cycle integrals of the omega GN and stuff like this, or?
So okay, what you would expect normally from doing non-perturbative TR, at least what I think you mean by it, is you directly construct an object which here contains integrals over B cycles. Here we're not doing that. So it's, in some sense, let me draw the spectral curve for you, at least very schematically. You have infinitely many nodal points. Let's say the origin is here. Here you have x equals to 1/4, 1, 9/4. And what we are computing is, first, we are performing these integrals of the omega GNs, which go from one sheet to the other. So this is minus z and z. And that's where we're performing this integral over I, which does something like this, passing through x equals to 1/4. So it seems like we are sort of closing the B cycle, but not really. So you don't obtain the same result if you, from the beginning, do the B cycle integrals here. And the reason, so we can of course discuss later because this might take a while, but the reason why we cannot do that directly is precisely because this pinched A cycle here. So if this was unpinched, we could just do directly the B cycle integral and recover non-perturbative results. But because of this pinching, there is some sort of regularization at play that leads to this weird integral. So the reason why we don't directly do B-cycle integrals is precisely the pinching. But this might sound very exotic, and yeah, I can give you more justification.
So thank you for the question and the talk. And there is a coffee break now, and we resume at 10:15.